Our speaker this morning is Tom Mrowka, who's going to tell us about an approach to the four-color theorem via Donaldson Floer theory.
So, like all of the other speakers, it's a tremendous honor to be asked to speak at Simon's 60th birthday. I was an undergraduate and then beginning graduate student just when people started to hear about Simon's amazing work, and I think it's hard, I think, for the young people today to understand just how exciting that period of time was. People were learning so much interesting mathematics, analysis, algebraic geometry, low-dimensional topology, and it was all coming together in this beautiful, amazing stew with theorems coming out left and right all the time. So, thank you for getting that ball rolling. And one other little anecdote or something. Raoul Bott once said that this is the graph of a typical mathematician's career. So this is research, this is administration and teaching, and this is, if you're lucky, prizes. So I think Simon has managed to do some kind of transformation of this picture where I think he doesn't do too much administration. But the research keeps going, and the prizes also, they go off the chart here. So, anyway, down to work. So Peter and I have been thinking about this for a few years now, about trying to use gauge theory to solve the four-color problem. A very dangerous thing to do. But let me try and tell you, so I'm going to tell you the sort of general setup, and Peter will tell you a little bit of the new things that we've learned a little more recently. So let me remind you about the four-color theorem. So there it is. Every proper planar graph admits a four-coloring of its complementary regions. It was first asked by Francis Guthrie, who was just trying to color the map of England and realized he could do it with the counties in England, and realized he could do it with four colors.
That's more than just England, Tom.
I thought people would let me get away with that with the fact that I used color in the British English spelling. Whatever. My spell checker didn't handle this very well. Anyway, so yeah, fair point. And it was actually formulated as a precise conjecture by Augustus de Morgan in a letter to Hamilton. This is actually a copy of that letter, and there's a little interesting bit. The more I think of it, the more evident it seems. If you can rebut with some very simple case, it makes me think that I shall have to do as the Sphinx did. So off himself if it was too easy. So anyway, that's a bit of the history. Of course, there's a long history of the four-color theorem. The first proof was by Kempe in 1879. Second proof by Tate. Must have been true by that point because there were two different proofs. Both of these proofs introduced interesting tools, combinatorial tools, Kempe chains and Tate colorings. But 11 years after Kempe's proof, he refuted his proof, but along the way he proved the five-color theorem. Peterson, a year later, refuted Tate's proof, and one of the interesting things that Peterson did was discover the Peterson graph. This is the Peterson graph. It's a quotient of the dodecahedron by thinking of the dodecahedron sitting on the sphere, quotient by involution. It admits no Tate coloring. I'll tell you what a Tate coloring is in just a second. Penrose, in his beautiful paper on diagrammatics of tensors, found a kind of algebraic reformulation of the four-color theorem. and then, of course, in '76 it was proved by Appel and Haken with the aid of a computer, and then that proof was much simplified by Robertson, Sanders, and Seymour and Thomas. And then in 2005, there was in fact, a computer-validated proof. So, you know, it's probably true. But there's no sort of human checkable proof available. So, the hook that gets us from gauge theory to the four-color theorem is via Tate colorings. So, we take a trivalent graph. Important notion for this is if we have a trivalent graph, or well, any planar graph or graph, it's called bridgeless if removing any edge leaves a connected graph. So this is a graph with a bridge. If I remove that edge, obviously it's disconnected. Okay, so now the reason the notion of bridgelessness is important in this important word to know in this discussion is because if you have a graph with a bridge, then its complementary regions are not a proper map. You have a country with a border with itself. Okay, so now Tate coloring is a three coloring. Again, this is Tate coloring of a trivalent graph. Is a three coloring of the edges so that when three edges meet, they have different colors. So here's the dodecahedron, and there is a Tate coloring of it. There are 60 such colorings, by the way, up to permutation, including permutations of the colors for the dodecahedron. And what Tate did manage to prove was that the four-color theorem is equivalent to the fact that all bridgeless planar trivalent graphs admit a Tate coloring. And that's rather easy. It's rather easy, first of all, to see that it's enough if your graph is not trivalent, it's enough. You can kind of perturb it to be trivalent, and it's enough to do the trivalent case. And just to see, it's an elementary and pleasant argument to see the equivalence.
Can you repeat again? What do you mean Tate's coloring again?
Tate coloring is the three coloring of the edges.
Three coloring of the edges.
Right, these trivalent graphs. Right, and the idea of the equivalence is that if I have my Tate coloring of the graph, I start on the outside and color that area white, and then as if I cross a green edge, I color green. If I cross another green edge if I have now a green region and I cross a green edge, it goes back to white. If I have a green region and I cross a blue edge, then it becomes red. And if I go from a green region across a red edge, it becomes blue. So this is the result of that procedure. And it's easy to see that that's consistent. Obviously, you're picking, you cross many different edges. There's different ways you could go, and it's easy to check that that's a consistent rule. Okay, so it's enough to find Tate colorings, three colorings of a trivalent graph. And let's make a definition that the Tate number of a trivalent graph is the number of colorings. And again, we're thinking of colorings. A permutation of the colorings we'll think of as being distinct for this purpose. And
you order the edges, you mean? Up to isomorphism, what?
You order the colors.
I order the colors. I order the colors.
Yeah. I mean, colors have some names, so they, yeah. Okay, so for the unknot, or the circle, the three Tate colorings, just the three colors. The Tate coloring of disjoint union is obviously the product of the Tate colorings of the individual pieces. The number of Tate colorings of a theta graph is 6, just the permutations of the colors, the three colors. The number of Tate colorings of the one skeleton of the cube you can check is 24, just for fun. And then I mentioned that Tate's coloring one skeleton of a dodecahedron is 60. So it's relatively easy to compute, and in fact, it has several nice combinatorial characterizations I'll mention because it'll come up later. One of them, which is due to Tut. So it's the unique number associated to a graph that if it's a circle, it gives you 3. If it has a bridge, it gives you 0. It's multiplicative for disjoint unions, and it satisfies Tut relation. So if I have four graphs which are identical outside of these disks and inside the disks, the four graphs look like this, then this particular alternating sum is 0. Okay, so you can always simplify a planar graph, it turns out, by these moves, and so but there are many others. So I want to change this into a problem in geometry, and a nice way to start to think about it is that actually, in a sense, the group law for the Klein-4 group has already appeared. You should think of the three colors as the non-trivial elements of the Klein-4 group, and then the rule for how I colored when I crossed edges, for example, is just multiplication of those guys. So you can think then of a three coloring as an assignment of the three non-trivial elements to the edges of the graph, and then the four coloring, you just start with the identity outside and then multiply your way in. So now I just said that again. So take coloring is just assignment of these non-unit elements to the edges. So if our graph is planar, then a simple reinterpretation of what a take coloring is that it's a representation of the fundamental group of the complement of the graph into the Klein-4 group with the property that if you take because it's planar, we can think that there are distinguished loops that go from some base point down to the plane and around each edge, and all of those distinguished loops have to go to a non-identity element. And the fact that it's a representation enforces the situation at the vertices. Okay, so there, a picture of what I just said. All right, anyway, so now that's starting to be something that's closer to our hearts. We like counting representations of the fundamental groups of contemplants of things. And the next little bit of geometry, so because every element of the Klein-4 group has square equal to the identity, actually such a representation factors through this quotient where for each of these distinguished generators that go around an edge, their square is 1. We can take a quotient by this, quotient by the things whose are the squares, so we set all the elements to 1. And we get a representation of this fundamental group. So there's a big literature in physics and in mathematics for dealing with trivalent graphs, and there's sort of a lot of interesting algebra around them. In that literature, you'd call the pair a three-manifold and a trivalent graph a web, and we might as well generalize this story to think of things to graphs that are not just planar. We could look at a knot. That's a perfectly valid graph from our point of view, or we could think of here's a knotted theta graph, but our graphs could be more complicated. The sort of important bit of geometry, that going back to this idea that these representations factor this quotient of the fundamental group, is that we can actually associate to a web, we can associate an orbifold. So what we're going to do so the idea here is that if I think of R3 acted on by the Klein-4 group, the quotient of R3 is still homeomorphic to R3. So if you quotient out by all plus minus 1 diagonal matrices, you'd get an octant. And you quotient out by half of them, so you get 2 octants glued together, and that's a copy of R3. But it's an interesting copy of R3. It's a copy of R3, so this is, it's a copy of R3 where the 3 coordinate axes collapse to a trivalent graph. So you know, so that, and that there's a, you know, similarly, if I think of, you know, the link of that picture in R3, I have this two-sphere with the 8 octants colored on it. After I collapse by the Klein-4 group action, I have 3 triangles, and I get the quotient is the 2, 2, 2 orbifold two-sphere. So, so if I see a trivalent graph in a 3-manifold, I can just think that that's the orbifold locus of an orbifold, right? And that's what I'll do. So we can do some orbifolding, and of course what happens. I mean, you know, orbifolds have a well-defined notion of the fundamental group. So the point being is, if I go twice around, because the edges here have order 2, if I go twice around an edge, that's supposed to be null homotopic in the orbifold sense. So there it is, null homotopic. So if I now introduce the orbifold fundamental group, then a coloring of a planar graph exists if and only if the orbifold fundamental group of the associated orbifold has a representation into the Klein-4 group, so that all of these edge generators are non-trivial. You know, so I mean, I haven't done anything deep, but I've certainly put the problem from something that was deeply in the world of combinatorics and put it pretty firmly into the world of 3-manifold topology. And in fact, an amusing and useless restatement, you can, you know, so a corollary of the 4-color theorem is that if, you know, if you have a planar graph, you can, there's sort of a good orbifold. There's a 3-manifold with an action of the Klein-4 group, so that the quotient is the 3-sphere, and the singular locus is your graph. Anyway. Yeah.
Why are you using planarity in all of this?
The only place I use, so mostly I'm not using planarity. The only point is that if I, you know, well, you know, I just wanted to know that the edges have a kind of unambiguous way of being corresponding to elements of the fundamental group as opposed to conjugacy classes. So just at the very beginning. So I mean, more or less I haven't. So don't worry about it too much.
Tom, could you explain again how you get from a planar graph to this orbifold? I slightly lost you.
So if
your graph is
I mean,
in 2 dimensions, and so you're putting it in R3. In what
yeah, it's sitting in R3. So I mean, just think of it.
R3.
I mean, but the planarity is not relevant.
Okay.
It's just that if I have a web,
Right.
a trivalent graph embedded in a 3-manifold, I can associate to it an orbifold.
And how do you do that?
And so that was the point that, well, so first of all, suppose I have a knot in a 3-manifold. I can associate to that an orbifold in many different ways where the knot is the orbifold locus. I need to tell you what's the multiplicity of that locus.
Right.
So now the multiplicity is always going to be 2 in our story. And the interesting issue is how can I make sure that that trivalent vertex has a good orbifold chart? Well, that's the point that R3 divided by the Klein-4 group is actually R3 again, you know, and in such a way that the 3 coordinate axes become, right, the 3 coordinate axes get folded in half.
For example, it's not trivial. We don't want it to be trivial, for example.
Yeah, we don't want it to be trivial. Yeah, so
Exactly the way Nietzsche gets it, not to be trivial.
yeah. It's not a, I mean, you know, that's really the orbifold locus, and I'm telling you that, you know, that the edges have order 2 group, and the vertices have Klein-4 group as a group. Okay, so that's the geometry. Now, of course, from the point of view of gauge theory, the Klein-4 group is not so interesting. What? What?
Very interesting.
Okay. Well, yeah, but not interesting. I mean, yeah, okay, it's interesting. Obviously, it is interesting, right? Because it has to do with the 4-color theorem.
As next to 2, we become the quaternion group.
Yeah, it does. Anyway, and so instead what we're going to do is look at representations into, the representation of the fundamental group into SO3, which of course contains the Klein-4 group, and see what that tells us. So, I mean, that's you know, standard bread and butter of Donaldson Floer theory, and what I want to make again a few more simple observations to motivate what's going on. First of all, you know, there's the annoying distinction that we always have to be careful about whether or not we're looking at representations or representations up to conjugacy, and representations have a little 0 up there, representations up to conjugacy don't. You know, yeah, so, and just as for a manifold, the space of representations, so up to conjugacy, has a reinterpretation as flat orbifold bundles, you know, so isomorphism classes of pairs, principal orbifold SO3 bundle, and flat connection. So from this point of view, actually, this condition that these edge elements go to non-trivial things are a way of pinning down actually the topology of the orbifold bundle. So you should think that that's you know, if some of them were trivial, we could have kind of erased them from our point of view, and but we don't want to do that. We want all the edges to be non-trivial. So that pins down the topology of the orbifold bundle. And for SO3 connections, those are the possible stabilizers. SO3 representations, those are the possible stabilizers. So the Klein-4 group can be the stabilizer. It's the stabilizer of a representation whose image is the Klein-4 group. That's important for the story. You know, so we're going to be more interested in the space of actual representations, not representations up to conjugacy. And then it's interesting to understand what the orbits of those, you know, of SO3 by these, the quotient of SO3 by these possible stabilizers. They give us what these representations lift up to, what conjugacy classes lift up to in based representations. So, what?
Is there a graph connected?
It could or could not be. You're worried about the topology.
The statement of node and edge non-trivial representation. Is that true for the graph or for just
Sorry. Edge non-trivial. Sorry. Yeah. Sorry. If it has a trivalent vertex, that's the. I mean, yeah. If it has a trivalent vertex, the stabilizer can be no bigger than the Klein-4 group. So yeah, thanks. Okay, so now I'm going to look at the same examples that I looked at sort of before and look at what the representation varieties are. So for the unknot, the representation variety is just RP2. There's essentially one representation, means one representation, and the based representations are just a copy of RP2, the elements of order 2 in SO3, and, well, the homology of RP2 has rank 3 equal to the number of Tate colorings. Now we're very excited. We look at the theta graph. Now the based representation variety is the space of three-dimensional flags. The number of Tate colorings is 6, and the rank of its homology is 6. Even more excited. We look at the trefoil. Representation variety has 2 components, a little complicated. Well, that's okay. We want to prove something about planar graphs. Trefoil is not planar, and when things are not planar, they naturally have more representations. Things become more complicated. For the cube, it turns out that the representation variety is a bit of a mess. If you look at the representations mod conjugacy, it's actually a Y topologically. If you work it out, and the base representation variety is a mess, number of Tate colorings is 24, but I mean, you could compute the homology, but it's a mess. For the dodecahedron, what you get is 10 copies of the flag manifold and 2 copies of SO3. So there are actually 2 irreducible representations and 60 representations into the Klein 4 group. 10 representations into the Klein 4 group, and then so here things start to differ in an interesting way. So the number of take-homes is 60. The rank of the homology of the representation variety is 68. Anyway, so yeah. All right. Yeah. Okay, so now we're going to do gauge theory on a principal SO3 bundle, and so we introduce the space of connection, orbifold connections on this SO3 bundle, look at the Chern-Simons function on that, and the critical points are gauge equivalence classes of flat connections, as we are used to from this sort of thing. So we'd like to use the Morse homology of the Chern-Simons function to define our invariant, but we want to the story looked much nicer if we worked with based representations, not representations of the conjugacy. And there's a little trick to do that. What we do is we take our original graph in our 3 manifold, and we take some ball, pick a base point, a little ball around it, and then stick a theta graph in it. Theta graph has a irreducible representation, and then we're going to work always with that kind of situation. We add this theta graph and then look at its representation variety and gauge theory of this associated web, not the original one, the one where you add the theta graph. And then there's still now a space of connections for this web, and now the critical points are the based representations. So that's great. So we want to define the Morse homology of this guy, and there's one sort of standard interesting point here, which is that actually that's one of the things it's important to have a kind of monotonicity condition to have nice compactness properties, that the value of Chern-Simons on loops, the Chern-Simons function, our Morse function, that's change along loops is proportional to the spectral flow. The Morse, sort of change in the Morse index around closed loops, and that turns out to be guaranteed by the choice of our particular orbifold. There's a little more interesting technical issue, which is that when you go through the bubbling analysis to check that d squared is 0, things go very nicely if you bubble away from the graph on the edge. And then there's a little interesting point if you bubble along at a vertex, or this is the situation now. You look at the 3 manifold times r, and you're bubbling along the vertex times r. Then there's some extra n's that correspond to that, but the n's come in multiples of 4. That's the stabilizer of the connection that's bubbled off. And so if you work mod 2, you still have d squared is 0. So there's, anyway, the theory that we're looking at just barely exists in a way, but it exists.
What do you do if you do it over Z?
We can't do it over Z. Well, actually, what? SU3 is okay because the codimension of bubbling in the SU3 story is higher. So the SO3 is the slightly delicate one.
Why can't you do Z?
Well, d squared isn't 0.
So if you have 4, it could have been
No, well, okay. Actually, I forgot off the top of my head if there's orientability, because it's always.
I'm really very confident that 4 was 1 plus 1 minus 1 minus 1 equals 0, but looking at some geometrical arguments, moduli basis from the force field, we kind of convinced ourselves that it was non-zero.
Yeah. So anyway, Okay. Anyway, but this is a mod 2 story. So yeah. So I want to state one of the interesting theorems that we know about this. So at the moment, you should realize that once we have this web in a 3-manifold, I get a Z2 vector space out of it. This Morse homology with Z2 coefficients of the Chern-Simons function on this associated orbifold. And one of the interesting, we can prove a non-vanishing theorem for this story in an interesting context, namely that if you have a web that is spatially bridgeless. So what a spatially bridgeless means, that's a kind of 3-dimensional analog of the notion of bridgelessness. So it's spatially bridgeless if there's no embedded 2-sphere which meets the web transversely in one point. So here are 2 different embeddings of the same eyeglasses in S3. This one, of course, so the eyeglasses has a bridge, but this embedding of it is spatially bridgeless. There's no 2-sphere that you can find that just hits this in one point. And what we can prove is that if you have sorry, this should be spatially bridgeless web, then the rank of this Floer homology group is non-zero. Okay, so that's great. And the idea of the proof borrows from our earlier work on property P and uses ideas of well, not sure what order I put these in, but Gijini, Gaibai, Ni, Juhas. And of course, actually in a kind of beautiful way, I mean, it relies on the sutured manifold technology, which in a sense goes back to Haken. So Haken still, in this line, would still appear. And the way spatial bridgelessness is used is to verify that a certain sutured manifold is taut. Okay, so and our conjecture, our hope conjecture, is that actually the rank of J sharp, for if you have a planar web, then the rank of J sharp is the number of Tate colorings. So if we can prove that, then we prove the 4-color theorem, right? Or if you prove that, you might prove the 4-color theorem. I mean, this is a rather, I mean, nice thing is that in any case, I've given you a Floer homology theory. Somebody should compute it, right? So that's a problem in modern day technology. Somebody should figure out what it is. If it's a number of Tate colorings, then that's the 4-color theorem. If it's not, well, I'm sure it's going to be quite interesting to figure out how to compute it. This is, of course, very different from any of the other kind of algebraic approaches where there's beautiful formulas for the number of colorings, but there's no way of knowing that that number is positive. So anyway.
What do you mean? What do you mean there?
Well, what I mean is that, like, if you look at Penrose has this beautiful formula for the number of colorings. You evaluate some state sum, and it computes the number of colorings, right? But how do you know that's positive?
I suggest that's an integer.
Yeah, it's an integer, and it could. I mean, it's non-negative because it's the number of colorings. That it's positive, yeah, Dini.
Will you tell us what happened to 68 versus 60 for the
I might tell you later. Yeah. I mean, it depends what time it becomes.
So you're saying the key is that you've proved the left-hand side is positive?
Yeah, that's right. So we know this number is positive in the case of a spatially bridgeless web, in particular for a bridgeless planar graph, but we don't know this. But we do know some things, so let me tell you some of the things that we know. So now, like with all Floer homology theories, it's not just an inert vector space. It fits into the TQFT kind of framework. There are natural 4-dimensional, 4 plus 2-dimensional gadgets that induce maps, and those things are called foams in the physics literature. Again, and if you look in the physics literature, so this is from a paper by McKay, Deutsches and Vaz, and many people, Havanov, Rosansky, Kapustin, Lee, many others have written about the subject of foams. And you're supposed to think of these as two complexes embedded in a four manifold. And they're allowed to have a very small number of singularities. So that they can either have, here they can have a singularity that looks like a y times an interval. And then along these edges, and then here and here there's a vertex where what the singularity looks like is it looks like the cone on the one skeleton of a tetrahedron. Okay, so at each of these vertices, there are 6 faces coming in. And that fits perfectly into our picture of orbifolding, because just as in the case, if I take the next dimension up analog of what I did in the three-dimensional case, if I take R4 mod, now the group of order 8 of plus minus 1 matrices which are in orientation preserving, quotient out R4 by that 8 element group, I get a copy of R4 again. Again, it's 2 now, what's the four-dimensional analog of an octant? Anyway, glued together along their boundary, and now the 6 coordinate 2 planes all get folded into there's a little more picture. So the 6 coordinate 2 planes get folded into these 6 half spaces with a corner on them, and there are 6 of them. There. I don't know why they move across the screen, but anyway, so. And another important aspect of the story is that I think all of the physics literature and mathematics literature, the foams have a kind of orientation thing. That's what the blue and the stuff before was. But we don't. For our story, there's no orientation. Our foams can be non-orientable. You could just have our foam could be just an RP2 embedded in S4, one of them, for example, or something more complicated. And
how about spin conditions?
there's no.
Well, you've got things that I think always get to double covering, and that gives extra parameters in favor. A lot more information.
It's possible, quite possible. But
Usually that's much deeper.
well, we've thought about things like that a bit, but haven't succeeded. Anyway, so the thing, what I want to say is that if you have a foam with boundary, so I think of this two complex inside some four manifold with boundary in such a way that the boundary of it is a web inside the three manifold, then this kind of thing, this is the kind of thing that induces a map. So I have this here, my two complexes embedded in the interval times S3. Then there's a map between the corresponding Floer homology groups. And these maps are obtained by counting solutions to the ASD equations on the corresponding four-dimensional orbifold. So again, just as in the three-dimensional case, I think of that picture as describing for me an orbifold.
Again, you're adding a theta graph things.
Yeah, and there's a theta graph times R sitting in that picture for the official definition of the invariant. And in fact, just as in the literature for foams, foams can be equipped with dots and decorations. What those mean for us is that those dots you can think of as defining real line bundles over the space of connections. So anyway, so you can, given those line bundles, you can cut down the moduli spaces by sections of them to get extra maps. So So a foam with dots defines a map as well. And now we can look at the unknot and the theta graph, and in fact, they're a little more interesting. They're not just, the unknot is not just, it looks more like RP, not, there's, if I just take the product cobordism and put dots on it, right, then there's an action of a little polynomial algebra on any of these 4 homology groups, or, well, a more complicated algebra if it's a web. And I can try to understand this group as a module over this algebra. And, so it turns out it's not too hard to show at the end of the day that, that as a module, the Floer homology of the unknot is just the quotient of polynomial algebra by u cubed. And now if I have more generally an interesting web times r, I can put dots on all of the corresponding faces. That gives me a little more interesting story. And in the case of the theta graph, remember the theta graph, its representation variety was the flag manifold, and these operators satisfy the relations of the cohomology of the flag manifold. So, so that's nice. And if you know Hovanov's construction of the SL3 homology, that starts to remind you of it quite a bit. It's and then if somebody has some good ideas, the first thing you should do is steal them. So we did, and try to see what you can.
Tom Lehrer song, plagiarize, let not escape your eyes.
That's right, let nothing escape your eyes. Yeah, right. So, but again, this is a story with Z2 coefficients, not with Z coefficients or C coefficients, as in Havanov. So there are a few rules motivated by that, what I said before, for evaluating foams. One of them, as in the Havanov story, is sphere removal. So map induced by this cobordism and a little standard 2-sphere sitting off somewhere with 2 dots on it is the same as if that 2-sphere weren't there. And a consequence of that is a neck cutting relation. So if I have a standard cylinder inside my foam, then, and that bounds a standard, some loop on it bounds a standard disk, which I can use to cut, then the J of the guy that contains this guy is the sum of maps induced by these 3 cobordisms. So I cut it and put 2 dots above, 1 dot on each side, or 2 dots below. Okay, and finally, J, if you have a pair of trivalent vertices and you can walk from one to the other along one edge, and you can get rid of them, and it turns out that those guys have induce the same map. So that gets you, well, and another thing you can prove is this bygone relation, J of a web that has a bygone in it is a sum of 2 copies of J without. The relation I mentioned of getting rid of tetrahedral points implies this triangle relation. If you have a triangle, you can get rid of it. By the way, those are all things that are true for the number of Tate colorings. And finally, most interestingly, there's the square relation, which if you have a web that has a square in it, then the J of this guy is the sum of J of these 2 guys, where you get rid of these edges or these edges. And a corollary of that is that our conjecture is true, for example, for bipartite planar graphs. So if you have a bipartite planar graph, you can always reduce it to a bunch of unlinks by these bygone triangle and square moves. So that makes you optimistic. And there are other interesting tools for computing these guys. There's
What color theorems are now
Yeah, it's trivial. But just a sec, you know. I mean, that's still. I'm not sure if you're supposed to think of that as a theorem about, analogous to proving a theorem about Seifert fiber spaces and thinking that you prove a theorem that's going to generalize to 3 manifolds or not. But I don't think so. I think that's, that's planar maps. Planar graphs are much more special. So, anyway, so there are other tools for computing these things, which there are exact triangles. So if I have 3 webs, L1, L2, L1, and L0, which are identical outside some 3-ball, and inside the 3-ball they look thusly. This picture is meant to emphasize that there's really a Z3 symmetry. This is the kind of picture you usually see in the literature where the symmetry is a little less clear. There are natural cobordisms between these guys given by adding they're kind of handle additions, but they're handle additions with a couple of extra disks in them. So here I've drawn the projection from 4 space into 3 space of a typical kind of handle. So this is supposed to go between, so between the red and blue picture. There's a, if this arc weren't there, there'd be an obvious one-handle cobordism. With those arcs there's still kind of one-handle cobordism. I push the arcs away so you can see there's an extra disk here and another extra disk there. Incoming boundary, outgoing boundary. So one of the computational tools that you can prove is that there is long exact sequence or exact triangle for these webs. The 4 homologies of these guys are related by a long exact sequence. And in fact, there's a little more you can prove. I could have also looked at webs that where, I might replace what's going on inside this 3-ball by, instead of these bits, or alternatively those bits, I could replace it by something simpler. Namely, there's no bar in them. And it turns out that there are, in fact, further exact sequences. So in this, the previous exact sequence that I mentioned had all 3 of the webs involved had a bar inside that ball. And it turns out there are exact sequences where exactly one of them has a bar inside that ball. So further exact sequences. In fact, they fit together in a nice picture like this. So whether or not the topology is like an H or a pair of I's inside the ball, there's 6 possibilities, and here they are. So there's an octahedral kind of picture that fits together, and the exact triangles. There are 4 possible exact triangles. The back one is the original one, the first one I mentioned, and then there are 3 others where there's 1 H and 2 I's involved. And it turns out that the remaining 4 triangles are commutative. So altogether, you've got essentially, a kind of instantiation of the octahedral axiom of triangulated categories. Ouch. Yeah, well, so the one nice reason for putting up this picture is that actually what you see around here, on the belt of this octahedron, those are the four things that were involved in the Tut relation that I mentioned earlier. So there are a number of interesting, here's it's equivalent to the previous conjecture, but another way of stating it, that if you have three planar webs differ only as above, then this alternating sum should be 0. The nice thing is that actually, if you look at the composites of these maps, the composite of any two of these guys is 0. So there's a little kind of little belt is a little chain complex, and you'd like to see that its Euler characteristic is 0. Yeah, that's this picture. And yeah. Anyway, so again, these four guys, the composites of any two of them is 0. And the other thing that we know is that the rank of the homology across this guy has the same rank homology. This one and this one have the same rank. This one and this one have the same rank. But the Tut conjecture means that all of those homology groups are the same. And it's a plausible conjecture, which is a plausible conjecture. This is a conjecture that you would hope is, if you just thought that the map between them was naively counting kind of some kind of colorings of webs. So you might think, okay, this homology group only counts the number of colorings, and then you could extend those colorings to the foams and count the number of ways that they extend. A plausible conjecture is that the homology groups of each of those vertices is actually 0. That's equivalent to the, that's kind of related to the hope that the maps are actually counting counting colorings that extend to the foam. Turns out that conjecture we know is false, and it's false for the dodecahedron. So if L1 is one of the edges, say, then and we know that this sort of strong conjecture doesn't hold. Yeah, that's actually my last slide. So I can say something about. So we, it might be that the dodecahedron is a counterexample, because in fact the rank of the homology of the representation variety of the dodecahedron is bigger than the number of Tate colorings. That there are these, there's 10 Tate colorings, so 60 copies of the flag manifold, and there are 2, turns out, irreducible representations, which give you copies of SO3, so a total of 68. We tried very hard and hopefully very carefully to figure out how to perturb the representation variety to make those guys, the unwanted ones, disappear. And if we did it correctly, they did. But, that's how shall I say it? That's the kind of thing that you just do in private. If the proof involves perturbing representation varieties, I'm not going to believe it. You have to figure out what's really going on. But we have some optimism that it's even true in this case, and Peter will tell you some other things that we know that may hopefully increase your optimism as well. So.
So you mentioned this SL3 one of homology for verbs.
Yeah.
Is that conjecturally the same, or
no? No, I mean it's well. So the SL3 homology requires, it's only defined for bipartite graphs, by the way. It needs, the webs have extra decorations on them and stuff like that. So these don't have any extra decorations. And it only works mod 2. It doesn't work otherwise, as far as we know. So it's related, but but of course we did prove that in the case that they both make sense, they kind of have the same rank for the planar case.
I suppose that
Yeah.
you could also consider the Euler characteristic rather than the rank of the whole homology.
Well,
That'll be something
actually,
simpler.
it got a mod 1 grading.
It doesn't have a
It doesn't
gradient.
have a mod 2 grading. It's kind of a runt, It's just barely there, and maybe it's like that, the sirens calling. We're just going to crash on the rocks, but yes.
You asked for helpful suggestions how one might prove your statement.
Yeah,
Can I offer some helpful suggestions?
of course.
Combination of 3 ideas. Here you're dealing with orbifolds,
Yes.
finite. There's a general principle by which you can always replace that by by a continuous group, connected Lie group, with finite isotropic groups.
Yeah.
Let's take that down. In this case, the connected Lie group with a circle. So you're having a circle. The second condition is is remember the theorem about moment maps and convexity, which many people have proved. On the torus action, the orbit of the projection becomes a convex polyhedron.
Yep.
Now, of course, that assumes the original space as one component. If you have several components, you get several convex polyhedrons, which don't altogether make a convex set. So my conjecture offering it to you is that this problem can be reduced to a question about, and of course, when you can't have convex polytopes, you can count things with integers. And so I'm conjecturing that you can transfer your problem into a problem about action of a circle, in the planar case. Otherwise, you'd have higher groups. Onto a disconnected connection of homogeneous spaces of algebraic. Nice algebraic, let's say, call them algebraic surfaces, which might be singular, and then they're a projection, and then you would count things like you count them for even rock and all against floor formulas, polynomials, and that would give you a technique. Which you could, of course, reduce modulo 2 at the end if you only wanted 2 results. But if you want something integers values, or more subtle, I'm offering you a program which you or your students can carry out.
Thank you very much.
This is obviously very exciting from an application point of view, right? I have a technological question.
Yeah.
So, again, you're telling us to deal with reducibles by changing the problem, preserving the topology, and getting rid of the reducibles.
Yeah.
Does that give you any insight of what we should actually do with reducibles?
No. No. I'm too old to deal with I don't have to. Maybe Simon's not. Yes.
If you have a bipartite graph,
Yes.
do you expect like a spectral sequence from the Havana SL3 homology to?
No, this is a SO3 gauge 3, not SU2. There's an interesting, there's an interesting story for the SU2 version. Where it's almost the same thing, but you have a slightly smaller gauge group. Only use determinant 1 gauge transformations rather than all. But even then, this, doing the SO3, the SU2 story eventually, the story which, well, yeah, for bipartite graphs you need extra data. I mean, to do the kind of SU2 story that you would hope. Sorry, never mind. It's the SU3 story that you might hope what you said is true. Not that.
Could I comment on SU2? Could I comment on the SU2 SU3 story?
Yes, you can.
The traditional way to deal with that is you don't forget, if you want SO3,
Yes.
you don't forget about the SU2. You take
No.
both together.
Of course.
And then you calculate the SO3 by subtracting two things. We did this back with Bode holiday.
Yeah.
You can subtract 2 from a power series and get a polynomial. And the power series are difficult because they have corresponding singularities. But never mind, you can't calculate in general the odd ones without doing the even ones. And then you have 2 instead of just 1, and there's your grading. You see, you gave it up because you focused on 1. That is in my paper with Bott, or friend Bott. He drew that nice diagram after. And a paper by Harden and Simon.
Yeah.
And it is a standard way to get calculations about the odd bits. You mustn't forget, you can't do it by, if you throw away the even bits, you're stuck, you've only got one hand. You said you only had one.
One grading.
Yeah, you've got to have both.
Well,
The other one is difficult, but the 2 difficulties cancel out and lead you to the good answer.
that would be great.
That's been done, you see. Read the literature.
Yes.
But you know, there is a whole spectrum of conjectures of high order counting of Hadwiger, yeah? You know,
Yeah.
how do they fit into the picture?
You know, I don't know. I mean, you know, they don't seem to at all, right? I mean, this is really something, you know, we managed to find some problem in 3-dimensional topology that has some kind of pretty close relation to the 4-color theorem. And it's really a problem, you know. I mean, the issue, I mean, the fact that you can do, you know, Floer homology to get topological control over representations of the 3-manifold is a very 3-dimensional thing. There doesn't seem to be an analog in higher dimensions.
No, it's not dimensional. They see this as a dimensional conjecture, like a combinatorial conjecture.
No, I know, but they're about polyhedra and higher dimensional polyhedra.
No, they about about graphs. No, they about graph is a properties when you exclude some, you know, you use graphs, and then there is a coloring conjecture of Hadwiger generalizing for color.
Oh, no, actually, I didn't.
It's
know
purely
that.
combinatorial. It's not about high dimensions.
I didn't. There's a different conjecture that I'd heard about, which is a sort of higher dimensional generalization.
No. It's not high dimensional.
Okay. Or maybe if you could explain what that
Yeah, well, I
is.
don't remember myself. Yeah, in some shape you see what else, you know, there are these huge graphs. Yeah, this is any planar graph corresponds to it contains, you know, full 5-point graph in this, you know, configuration of sigma. This hierarchical graph like that, and for each of them there is a coloring conjecture.
Yeah, no, I don't know.
So we should probably eat indeed. So before we thank Tom again, Richard, are there instructions about lunch today? Because it's here and it's now, right?
Yeah, we're just going to eat out there. There's a buffet, and then things will evolve. We'll see as we go. Yeah.
Okay, so let's thank